phone call came. Okay. I got to get another webcam. All right, these natural fluctuations in reading. Some readings are a little high, some readings are a little low. So, how do you eliminate random error? Have you had any? Let's say we're taking a measurement of length, and one person reads here, another person reads here, the same object, right? And so which one of these is accurate? What is accuracy? Well, somebody had the answer yesterday. What was accuracy again? Or I think somebody, was it this class? They take 3 measurements. Which one of these is accurate? Do you know? Or actually, let me back up a step. What is accuracy? Versus precision. Did I talk about this yesterday? Accuracy and precision? You know, what tends to happen is people forget about accuracy and precision until the day right before the final, and then start studying it. And then, you know, that results in very high stress levels. You build up a lot of stress chemicals. That's the way I used to study all the time. I still do stuff like that. I like to procrastinate, but as a student, I was trying to be more disciplined and not, you know. And that way, accuracy and precision wasn't long lost. You know, that was a month ago. How much stuff do you remember from a month ago? Do you remember, you know, what you had for breakfast from a month ago? You know, what you did Monday a month ago. You know, it's hard to, right? But I don't know why people expect that they can just review it quickly and see. And so it's like repetition. This is why I do repetition. I do repetition not to be, not to subject you to this, you know, to make chemistry tedious, but just repetition just to reinforce, so you can try to get it into your memory, right? And so what is accuracy? And what is precision? Just take a guess, a wild guess, because there's no penalty guessing. Unless this is a test. Uh-huh.
Is accuracy the number of times you hit on the dot, and then precision within the region?
Accuracy doesn't have to do with the number of times. You know, it can be related to the number of times, but accuracy, you know, this is the dartboard analogy in Chem 4. In Chem 4, go back in your book and take a look. They have the dartboard analogy there. You throw 3 darts. One dart lands here, another dart lands here, and another dart lands here. What can you say about accuracy? We wouldn't take accuracy, you know, what we do is we look at, was this dart throw very accurate? Accurate meaning bullseye. Did it hit the bullseye? No. Did this one? No, but this one was highly accurate. And so this wasn't accurate, this wasn't accurate, this was accurate, right? We do accuracy in 2 ways. One, we look at the individual measurements. You know, which ones were accurate, which ones weren't. The other is we look at the average. When you average those 3 darts, what do you see? When you average this, where would the average lie? We average this, right in the middle. And so the average looks pretty accurate, right? And so when we're thinking about accuracy, we have to keep these things in mind, because let's say, you know, this is dart thrower A, and then we have dart thrower B. Okay, for dart thrower B, let's say they do one dart that came out here. This is for B. And another dart came out here. And the third dart came out here. Was dart thrower B very accurate? No, I mean, none of the throws was very accurate when they're trying to hit the bullseye. But where does the average lie? Where does the average lie? The average lies in the bullseye. And so the average is quite accurate, right? Would you say, wow, the average for dart thrower A and the average for dart thrower B were right on the bullseye, so both of them have equal accuracy. True or false? They both have equal accuracy. True, right? A and B, the average, are right in the bullseye. What more can you say? But do you see a problem there? There's a serious problem here. The serious problem is, who do you trust more? You know, to throw, who would you trust? You trust A much more than B, because B just got lucky. You know what? B got lucky because it was only 3 throws. If it was 2 throws, right, where would the average be? Down here. If it 3 throws, it was right in the middle. 4 throws, it would have been way out here, right? And so B just got lucky. And we only limited it to 3 throws because on the 4th throw, who knows what would have happened. But here, the 4th throw would have probably been around here and changed it a little bit, right? And so we have to look at this also in terms of, normally when we take a look at these things, we look at the average, but we also have to take a look at something called what? And precision. And precision. So here, you know, when we look at the precision here, precision is not good. What is precision? Well, what precision is how well each measurement, each throw agrees with each other. If it's a tight range, then that's high precision. If it's a very wide range, we call it low precision. It's the same thing in measurements. You know, if you take a 1 milliliter measurement, it's a wide range. You know, because it can be anywhere from a half a milliliter to 1.4 milliliters. Whereas at 1.00 milliliters, it's a tight range because it's only 1.004 down to 0.995 milliliters. And so here, when we look at, we have to think about these two things together. Whenever we see an average, we got to think, well, what kind of precision was there? You know, and so this brings up random error. As long as there's no systematic error, you know, as long as the bullseye isn't off or something like that, that would be a systematic error, then you know how both of these can be accurate? The way we can eliminate random error, is by throwing, like if dart thrower B threw an infinite number of darts, you know what the average would be? If dart thrower B threw an infinite number of darts, the average would be right in the center. Okay, because you know some are off left, some are off right, but you'd figure after an infinite number of throws, the average should be dead center as long as you know the target didn't move. There's no systematic error. Right? And so this is how we can eliminate random error. We take an infinite number of measurements and then average those. That's how you eliminate random error. But can we take an infinite number of measurements? No, and so we have a finite number of measurements, and the typical number is 3. You know, the typical number is 3 because there's a trade-off in statistics. You know, because we'll do statistical analysis of this. We just don't write the average, but we show some kind of measure of the precision. Well, how do you represent this measure of precision? We use statistics to do that. And so when we do statistics, we do this. Here. We report the average plus or minus some kind of range. This range typically is the 95% confidence limit. And so in science, whenever you see measurements and averages, those are usually associated with a plus or minus. In fact, they're always associated with a plus or minus. In Chem 1A, we don't want to put too much onto the students, so we'll eliminate a lot of the statistics that are associated with measurements. But this is some of the most important stuff, because you have to know how good your numbers are. You know, how much confidence. I mean, you know, you could have junk numbers. You know, the junk numbers would have huge 95% confidence limits, saying you don't have much confidence in this number. It's not a problem, you know, as long as you recognize it. But if you didn't have this, you don't know, is that average good or is that average junk? Because this average would be more garbage, right? Because the you know, this average, even though it's highly accurate, it was just luck, you know. Because the 95% confidence limit here is going to be big, and this is going to be small. And so we have this 95% confidence limit tells us about the precision, you know, of this. We'll be talking more about this as we go along, but this is just an intro. You don't have to worry too much about the 95% confidence limit now. For your formal report, we're going to be doing this. You know, we're going to be generating some statistics on the your analysis. And we'll talk about it at that time. You're going to incorporate that into your formal report. For this, for right now, you know, some things we don't know, you know, how good those particular things are. And so let's go back to the problem number 67 that we're looking at right here. And I saw, oops, this is, I saw the a number of you registered for Piazza. That's great. Looks like maybe about 10 of you. For the others, I sent out an invitation. You just click the link in the invitation. Register for it. All right, so again, what is accuracy? Uh-huh. Yeah. Yeah, good. It's how close the measurement or the average is to the true value. So we have accuracy of individual measurements, and some inaccurate, some accurate, as well as the average. What is precision? Anybody else? Okay, go ahead. What's your name? Stanley? Okay, Stanley, please.
How close the number of measurements
How close? Yeah, good. What's your major, Stanley? Mechanical engineering? Okay. Well, as a mechanical engineer, you'll get plenty of this. So, did you already have some of this in physics? Did you guys? At UCLA, they do a lot in their general chem. Do every single lab report. Need to analyze error analysis. Not error analysis like, oh, I made a mistake here, I spilled this, I spilled that, I could have done better here. No, error analysis involving numbers, you know, what the maximum error in each measurement is, and how those propagate through the experiment. Unfortunately, when you compare, let's say, when you compare us to UCLA, well, unfortunately, that's one of the weaker points from taking Gen Chem here versus Gen Chem there. You would have gotten a lot more error analysis there. And so that's why on the formal report, I'm going to ask you to do some. You know, this goes beyond what the report does. Okay, I saw some of your books, and they came bundled with this website, which is Mastering Chemistry. And it's an online homework. But they have a little more than just homework. They have some quizzes on here, you know, multiple choice quizzes, videos, and other resources. So if you decided to get this in the bundle, you can use it. You could use it for other classes too. Wouldn't hurt to get a little bit familiar with this because I heard UCLA biology and UCLA physics uses it. You know, so if you got a little familiar with it, you got a little head start. I used to use it a lot, but I got a mixed feelings. Can you guys see this okay or not? You try to raise it up a little bit? All right. What is this an example of? An empirical equation. Where do empirical equations come from? Empirical equations come from laws? They don't come from laws. Empirical equations are often laws. Like this would be the law of the density para-dichlorobenzene. But in order to be a law, what would you expect? In order to be a law, there must have collected a lot of data. You know, not just a couple of data points, but a lot of data. What else? Well, where do they come from? Well, this is another advantage to to reviewing every day. If you review every day, then you aren't overwhelmed because the number of new topics we're going to cover. Right now I'm going slow, but I'm going to not review as much stuff. I'm just going to move on through this stuff because we don't have that much time. I'm supposed to get through 2 chapters this week. So that way, if you covered it yesterday, at least, empirical equations come from where? Well, tell me what the scientific method is. At least, do you have that memorized? You start off with observation to patterns, trends to laws to hypothesis. Okay, good. You have that one. Yeah. And then laws are often these just mathematical equations that describe the pattern. Right? We have some kind of pattern. The pattern, this graph is kind of interesting because what would this graph look like? First you collect the data, the XY data, right? You get the XY data, you have a whole bunch of numbers, and then you plot, you plot Y versus X. In this case, Y is going to be the density, X is the temperature, right? And so what does this plot look like? Well, this plot looks like, okay, here, looks like the temperature is less than 15. Is this Celsius? This has got to be Celsius, right? I think. One thing that I hate about this equation. What do I hate about this equation? There's no units. This is like an engineering equation. I told you engineers, they don't want to be bothered with a lot of stuff. But in chapter 1 they talk about that engineering disaster that happened to the satellite or whatever. Where some engineers were working in English units and some engineers were working in metric units. But they didn't know because all the equations are like this, no units. But for us in chemistry, we're always going to put units in there for our equations. It's very important to put the units in because you could, I don't know how many points I've knocked off because people didn't keep track of units. They made such simple mistakes that would have been caught immediately had they used units. They're getting units like the most bizarre units, a milliliter cubed. What the heck is a milliliter cubed, Just weird stuff. Anyway, unfortunately they didn't, but anyway, looking at this, if the temperature is less than 15, this goes negative, so it looks like the density actually increases up to about 15, right? And then if this goes above 15, then this goes positive and this is negative, so the density actually decreases. And so we get a weird mathematical function like this, right? But there's data. Somebody took measurements and measured the density and watched how it behaved. Correct? Maybe it's more like this, looking at this particular function. But normally we expect something like this, kind of fit to that. And so they have all this data. Well, the best representation is this mathematical equation, but how well does this mathematical equation fit the data? That's a matter of statistics. We're going to be covering some statistics, and usually we represent it with something called an R-squared value. R-squared value tells us that the mathematical equation fits the experimental data perfectly. You get an R-squared of 1. Not so perfectly, you get lower R-squared values. We don't have that here. Normally you have an equation here, you'd write an R-squared. And so there are certain things that are done in Chem 1A we eliminate certain things to make your life easier, right? We eliminate all this error analysis. For example, you don't see a whole bunch of plus or minuses, but if you look in the literature, you see an equation like this, you'd see plus or minuses here, and you see r squared here, right? It's just standard. That's what's done. When you're given the average, you're always given 95% confidence limit. And since error analysis is covered in Chapter 1, that's what I'm going to cover now, and this is something we should think about as we're going, and we're going to think about it in one particular experiment. But anyway, for this particular thing, we derive an empirical equation. I want you to derive an empirical equation. Can you do that for me? Let's derive an empirical equation. This is going to be... this is what we're going to call a practice quiz. I told you I'm going to give pop quizzes, right? And so this first one's going to be a practice. And so your quiz today is you're going to derive an empirical equation that's going to describe this data for me. Okay. And in this particular quiz, you know what we're going to do is, and this is the way I'm going to make the quizzes this semester. You can work with your partner or with your neighbor or whoever. This will be group quiz. The exams aren't going to be group exams, but the quiz will be, okay? And so this you can just work with whoever's around you, or you can work by yourself. I don't care. A lot of people prefer to work by themselves. I want you to take this data. This data is going to be, let's go temperature in degrees C versus temperature in degrees Fahrenheit. And we're going to have 0 degrees C, 32 degrees Fahrenheit, 100 degrees C, and 212 degrees Fahrenheit. Okay, take this data and generate a mathematical equation that describes this. Do you see a pattern? Do you see a trend here? Okay, what is the pattern? What is the trend? Do you know what a trend line is? Well, that's a hint. And then come up with some mathematical equation. You might already have it memorized, mathematical equation, but let's do this and then we'll go on break. So let's take 5 or 10 minutes for this. Stop.